Okay, in this next video, I'd like to take a look at cholesterol disposal. So in the previous video, we examined cholesterol synthesis, and an important feature to notice about cholesterol synthesis is the enormous amount of NADPH plus acetyl-CoA plus ATP that goes into forming cholesterol. What this means is that we have a large amount of our potential energy stores being used to form a very complex molecule of cholesterol. Now, an interesting fact about cholesterol is that once we make cholesterol, we cannot break this down to generate energy. We've seen that when we store all of our acetyl-CoAs in the form of fatty acids using lots of NADPH, ultimately we can take this and we can derive energy. So the storage of energy as acetyl-CoA and fatty acids is reversible. So we can extract back the energy, we don't lose it. But with cholesterol, we cannot do this. And the reason for this is because of the ring structure. The ring structure of cholesterol, we do not have any enzymes that can break these rings. So this is why cholesterol is very tightly regulated and controlled in its biosynthesis. Now, once we have cholesterol, there's only two options for us. One is that we use the cholesterol, and the use of cholesterol, recall we use them in plasma membranes. This is to control the fluidity of membranes, and importantly, we use it in steroid synthesis. Now, if we do not use cholesterol, we have to dispose of cholesterol. Now, this video is about cholesterol disposal. How do we get rid of cholesterol in our body? Now, this applies for both endogenously synthesized cholesterol in the liver and also cholesterol obtained from our diet. So the first step is to take our cholesterol and we are going to place it into a pathway that is exposing it to an enzyme called 7-alpha hydroxylase. Now recall that cholesterol already has a hydroxyl group on it. This is in the number 3 position. On the A ring. And the first step of cholesterol synthesis, cholesterol disposal, is to convert this, not to leave the 3-hydroxy there, but also to add another hydroxyl group. And so we are now generating 7-hydroxy cholesterol. The reason that this is an important step is that this is the committed step into cholesterol disposal. So this step is not reversible. Now, once we have our 7-hydroxycholesterol, there are several steps of modification. And these steps include another hydroxylation reaction and also a shortening of the hydrophobic tail of the cholesterol molecule, which is on the D chain. The other addition is we are going to be charging up the molecule by adding a coenzyme A. So what we are essentially forming are two independent molecules. One is called shenodioxy cholyl-CoA, shenodioxycholyl-CoA, and the other one we're forming is cholyl-CoA. The only difference between these two structures is one hydroxyl group. So the cholyl group has a third hydroxyl group in addition to the number 3 and number 7. The shenodioxycholyl lacks this hydroxyl group and only has hydroxyl groups on 3 and 7. The differences in structure and properties of these is not that important, but just to know that these are the two products, intermediates of cholesterol degradation. Now, the next step for both of these is going to be what's called a conjugation reaction. The reason this conjugation is done is primarily to increase aqueous solubility. Recall that the cholesterol structure has the hydrocarbon ring structures, which are very hydrophobic. The hydrophobicity can cause chemical problems in disposal of cholesterol. What is going to happen is that these products of this conjugation are going to be stored in the gallbladder. The gallbladder, recall, is a small sac that can hold a large amount of material. And if we have a lot of hydrophobic molecules in this small space of the gallbladder, we can cause precipitations. These precipitations, of course, are known to us as gallstones. So the majority of gallstones that are found in the gallbladder are due to cholesterol. So the conjugation reaction is going to increase the aqueous solubility to prevent gallstone formation as we store this waste product in the gallbladder. What we are going to be adding onto this structure, both structures, is one of two amino acids. We will be adding either this molecule, glycine. Notice that adding glycine to this structure, we are adding a carboxylic acid, which is going to dramatically help with increasing aqueous solubility. The other structure that we will be adding is this structure. This is called taurine. And taurine, any of those of you that are familiar with cats, this is a required factor, modified amino acid, for vision for cats in their eyes and their retinas. So by either conjugating these molecules to shenodioxycholyl-CoA or to cholyl-CoA, we will be generating the respective molecules called glycocholic acid. If we attach glycine to, say, for example, cholyl-CoA, or taurocholic acid, if we add taurine to cholyl-CoA. And of course, the reaction of this conjugation will release our coenzyme A, which is the energy, the hydrolysis of that thiol ester, the energy that drives this conjugation reactions. Now these products will be secreted from the liver and stored in the gallbladder. Not to leave out shenodioxycholic acid, is that if we conjugate shenodioxycholic acid with either glycine or taurine.
Hi, this is Rob. I can't get to the phone right now. Please leave a message and I'll get back to you.
If we conjugate the glycine or taurine with shenodioxycholic acid, we will have the same molecules with the different names, glycoshenodioxycholate or tauroshenodioxycholate. Now, once this is stored in the gallbladder, during the meal, the gallbladder will send this material stored into the intestine, specifically into the duodenum. These molecules are more familiar to us as bile salts. So once these molecules are in the intestine, they serve two functions. One is to increase the solubility of fats from our diets, and the other is to dispose of excess cholesterol. So the primary chemistry that the bile salts are doing in the intestine is to form what are called micelle structures. The micelle structures are the bile salts intercalating into fat droplets that we have in our intestine from our diet. What this does is it increases the surface area for lipase activity. Now recall the lipases come from our pancreas, and during mealtime, the lipases are to digest triglyceride structures in fats to release the fatty acids for uptake by the body. If we have large lipid droplets from our dietary fat, we only have a certain amount of surface area for the lipases to work on. So what the bile salts are doing is a process called emulsification. This is not a chemical change as far as breaking bonds, but all we are doing is that these bile salts, with their hydrophobic ring structures, are intercalating and wiggling their way into these lipid droplets in order to increase the number of droplets, making them smaller, and thereby increasing the surface area. Now, by increasing the surface area, the majority of these lipid droplets now have greater exposure to lipase in order to release those fatty acids. Now, the other purpose of putting bile into the intestine is to dispose of extra cholesterol. The way this works is that the bile eventually become what's called deconjugated. Deconjugation simply means that the glycine or taurine structures that have been added onto the cholic acid or shenodioxycholic acid are removed, and these are removed by bacteria in the gut. So therefore, instead of having bile salts, we now have bile acids. And these bile acids are taken up by a certain portion of the intestine. And this location is at the terminal ileum. The terminal ileum, of course, is the last portion of the small intestine. In fact, approximately 95% of the bile acids that are present in the gut from the original secretion from the gallbladder are taken up by the N-terminal ileum. What that means is that 5% is found in feces. So for every round that we have of storage in the gallbladder, secretion in the intestine, 5% of this material ends up in the disposal process. 95% is taken back up into the body. Once this is taken up into the body by the hepatic portal circulation, it's returned to the liver. And there, the liver undergoes the conjugation reaction again and sends this into the gallbladder for another round of secretion. Now the question is why is this? Why do we only lose 5%? We'll go back here about how much energy it takes to generate cholesterol. Our diets were not always high cholesterol diet. That is just an advent of the Western diet. So when we have a limited amount of cholesterol in our diet, we have to synthesize what we need. And we're putting so much energy into it that we want to make sure that we are recovering a sufficient amount in order to continue its role in digestion. If we had to keep generating the bile salts from new synthesis in order to facilitate this reaction, we would be shifting a lot of acetyl-CoA from our energy production pathways or energy storage in fatty acids, which is going to help us in the fasting state, shifting that into cholesterol, of which we can never extract that energy back out. So by recirculating our cholesterol as bile, that allows us to recover this precious structure that we put so much energy in and reuse it. So this is the reuse of cholesterol. However, we do have to have a mechanism of disposing cholesterol, and that is the 5% that is disposed in the feces. So with enough rounds of cholesterol synthesis into cholic acid and chenodeoxycholic acid, and enough rounds of secretion from the gallbladder into the intestine, eventually that 5% will make a significant difference in the total systemic body's pool of cholesterol.